wave equation. Okay, before going to that, let us see these things. Okay. What do you see on the top, or to say top rectangle? Omega is equal to 2 pi nu. K is equal to 2 pi by lambda. What is omega called? Angular frequency or angular velocity, whatever you want to call it. Okay, because omega is equal to d theta by dt. Okay, or I can call it as 2 pi nu or 2 pi n. Okay, where n is the frequency. N is the regular, okay, normal frequency, and 2 pi is the angle part. So 2 pi nu gives you angular frequency. Omega is equal to 2 pi nu. Okay, right. K is called the propagation vector. K is called the propagation vector, which is actually equivalent to 2 pi by lambda. 2 pi by lambda. Okay. Now let's look at this one. H cap omega. What is H cap? H cap is nothing but H by 2 pi. H by 2 pi. Okay. So H by 2 pi into omega. That is 2 pi nu. So H by 2 pi into 2 pi into nu. So 2 pi get cancelled, and what do I get is H nu. H nu is again energy. So that way H cap omega gives me energy. Exactly in the same way, H cap is H by 2 pi and K is 2 pi by lambda. So what do I have? H by 2 pi into 2 pi by lambda. So what do I have is H by lambda. H by lambda is momentum P. Okay. Now this, okay, is something which you need to understand. To understand Schrodinger. Okay. After that, let me go to the basic aspects of quantum mechanics. Okay, in quantum mechanics, every particle, quantum mechanical particle, is represented by a wave function. We have seen already that every quantum mechanical particle is represented by a matter wave. If it is represented by a matter wave, then there should be a mathematical function representing that wave, and that is what you call it as the wave function for that matter wave. And it is generally represented by the symbol psi. Okay, that's what you see here, psi. Okay, the yellow box. Okay, psi of x comma t, right? That psi is your matter wave. Okay, that is the general way. Okay, sorry, if I want to represent it in a different way. Okay, it's up to you. But okay, name it. Okay, tell it that it is the wave equation. Okay, matter wave equation. Okay, so every quantum mechanical particle can be represented by a wave function, and the particle wave function is represented by a plane wave equation. So will that be any equation? No, it should be a plane wave equation. What do you mean by plane wave equation? When you say a plane wave, that implies you have a set of waves traveling in the same direction. You have a set of waves traveling in the same direction. So that's what we said when we were talking about matter waves. We consider that we have, okay, matter wave, or to say wave packet consists of a large number of waves which are traveling in the same direction, Because they are traveling in the same direction, I am considering them to be a plane wave equation. Okay, so I am considering that the matter wave function is represented by a plane wave equation. Good. After that, any physical observable value is derived through using an eigen operator. What is this? Nothing. When you say you have a matter, you should be knowing its position. You should be knowing its velocity. You should be knowing its kinetic energy. You should be knowing its potential energy. Okay, these are some of the things that you should be knowing about the particle. Now, these are called the observables. That means that can be observed by an observer. An observer can observe the position of the particle, can observe the velocity of the particle, can observe the kinetic energy of the particle, can observe the potential energy of the particle, can observe the frequency of the particle, something like this, okay, or momentum of the particle, and so on, so on, so on. So all these physical variables are called physical observables. Okay, so if you want to know the physical observable of a matter which is being expressed as a plane wave equation, then you need to use an eigen operator. Why eigen operator, sir? Why not only operator? Or if you take any operator may change the plane wave equation. If it is changing the plane wave equation, that implies you are changing the matter nature. That means the nature of the matter. That means you're not finding its state as it is, but you're disturbing it. So you don't want to disturb. If you don't want to disturb, that means the plane wave equation should not change even after the operation. If the plane wave equation is not changing even after the operation, that implies the operator must have been an eigen operator. Okay, right. With that, we see that the plane wave equation is represented by psi of x comma t. Why x comma t? Because the plane wave is depending upon position as well as time. It may be depending upon position as well as time. Please remember, when it is dependent upon position, that implies you are indirectly talking about momentum. When you're talking about time, that means you're indirectly talking about energy. Because you have seen that Heisenberg's uncertainty principle makes this position and momentum pair variables, and energy time again another set of pair variables. Okay, so psi of x comma t is the wave function, but this has to be a plane wave equation. Because it has to be a plane wave equation, the right side part tells you what kind of equation it has to be. That is a e to the power of I kx minus omega t. Okay, right. Now this is the plane wave equation for a particle traveling along the positive x direction. For a particle traveling along the positive x direction. Okay, right. This a to the power of I kx minus omega t can be written as a to the power of minus I omega t into psi of x, where psi of x is just a to the power of I kx. Psi of x is equal to a to the power of I kx. So this way, what did I do? I am trying to separate the variables. That's it. Okay, right. Now, let me just rewind this. Every quantum mechanical particle has to be represented by a wave function. And the wave function should be a plane wave equation. And if you want to find out any physical observable value, if you want to find out any physical observable value, then you have to find an eigen operator, suitable eigen operator, operate it on the plane wave equation to get the physical observable value. That's what is your eigen equation. Operator O acting on the wave function x, giving you the value of the physical observable lambda, keeping the wave function unchanged as x. Okay, right? So psi of x comma t is the wave function based on position and time. So as I said, x and t are not state variables. Okay, now 5 seconds for a question I'm asking now. Instead of x comma t, what can I take in their place? Instead of x comma t, what can I take in their place? 5, 4, 3, 2, 1. Okay.
L comma theta, sir?
No. Because x and L are not pair variables. See, I'm taking x and t. X and t are not pair variables. What's a pair variable for x? 5, 4, 3, 2, 1.
Position.
Momentum. X is the position vector, so its pair variable is momentum vector. Similarly, what is the pair variable for time? 5, 4, 3, 2, 1. దేవ దేవ ధవళాచల మందిర గంగాధర. ఏంటమ్మా మీరు ఇట్లా ఏమి ఓకే రివైజ్ చేసుకోకపోతే చాలా కష్టమ్మా. యూ విల్ నాట్ ఎంజాయ్ ఫిజిక్స్. ఒకసారి రివైజ్ చేసుకుంటే చాలు. ఇక్కడ ఏ పెద్ద బై హార్ట్ చేసి చేయాల్సింది ఏం లేదు. X, Px are state variables. That means position and momentum are state variables, energy and time are state variables, right? X place lo Px, okay, P and E, T place lo E kuda rayachu. Psi of E, T or psi of P, T kuda rayachu. Okay? Psi of X, T rashinattu psi of P, P, E kuda rayachu. That's all. ఓకే ఇదేదో కొత్త కాదు. సారీ ఐ థింక్ నెక్స్ట్ సెమిస్టర్ లో వస్తుందా? ఓకే 4 year సిరీస్ వస్తుందా? ఐ మీన్ 4 year ట్రాన్స్ఫార్మ్స్ అవన్నీ వచ్చాయా ఇప్పుడు? మీకు మ్యాథమెటిక్స్ లో 4 year ట్రాన్స్ఫార్మ్స్ వచ్చిందా?
No, sir.
ఓకే సరే. ఓకే సో అక్కడ తెలిసిపోతుంది. అక్కడ యూ విల్ కమ్ టు నో అబౌట్ ఇట్. ఓకే సరే అప్పటికి వెయిట్ చేద్దాం. సరే ఇక్కడ మామూలుగా కూడా చెప్పొచ్చు. సరే ఐ ఆస్క్డ్ ద క్వశ్చన్. అది మనకు కంపల్సరీ కావాల్సిన క్వశ్చన్ ఏం కాదు, బట్ రివైజ్ చేసింటే మీకు అర్థమయ్యేది. Psi of x, t can also be represented as psi of p, e. అది కంపల్సరీ క్వశ్చన్ కాదు మీకు. ఓకే ఈ డైరెక్షన్ లో ఎట్లాంటి క్వశ్చన్స్ ఎగ్జామ్ లో కూడా అడగము, బట్ ఓకే కామన్ సెన్స్ కోసం. ఓకే సో psi of x, t is a to the power of I k x minus omega t. Okay, dou by dou x of psi of x, t is I k a e to the power of I k x minus omega t. Okay. Now, if I take I h cap on both sides with a minus sign, then on the right hand side I'll get h cap k. But h cap k is momentum. So minus I h cap dou by dou x is the operator when operates on the plane wave equation representing a matter wave, then it will give you the momentum of the matter wave. In the same way, if I differentiate, okay, if I apply the operator I h cap dou by dou t, if I apply the operator I h cap dou by dou t, then I get energy of the matter wave. So I h cap dou by dou t is the eigen operator for total energy, and minus I h cap dou by dou x is the momentum operator. Okay, yeah, I'll stop it for today. So